So, like I said, last time we talked about entropy produced terms. And today what we're going to talk about is isentropic processes. Now you might be going, well, I'm going to do an impression of you. Well, Jared, we already talked about isentropic processes, right? That is true. We have, but not to the same degree at which we need to go into it even more, because the way that this class, at the end of it, and in your next class in Thermo 2 works, is that isentropic processes are the basis of all of the essentially all of the analysis that you do of like every cycle, right? Like we're talking regular Rankine, which is how your power is made down there in Carbondale from the Lake of Egypt power plant, to any other type. It is basically Rankine-based cycles. Then there's some other ones that are like, natural gas, but you'll get into more of those later. But essentially, they all work the exact same way. How you do your analysis is isentropic processes. So we're going to start there. So as you guys remember, isentropic process means that constant entropy. So S1 is equal to S2, right? So before the process, you have an entropy of one value. It is the same after the process. And what that generally means is that, or if you guys remember, delta S had to be equal to this Q, or this Q term over T, B plus sigma, right? If you guys recall, what this delta S essentially means is that, or isentropic means, is that essentially the process created no entropy, right? It generated no more entropy. And there was essentially no relevant heat transfer in the process, which means that if you expand this, you get S1 is equal to S2, right? So that is the background, just to be sure that we are on the same page. And it says the object of the present section is to show how properties are related at any two states of a process in which there is no change in specific entropy. All right. So right here, this is a TS and HS diagram showing that what it looks like when you have constant specific entropies down. So right here, this is a very common setup for Rankine cycles in this class. So a lot of times, so this is not a basic Rankine cycle. This is a looks like open feed or closed feed water heater. So what essentially what an open feed and closed feed water heater system looks like on your drawing is, so this is I'll draw it really fast just so we can you understand what I'm talking about. So this is a boiler. You have a turbine stage right here, and then in between another turbine stage, some of it gets brought out to a heat exchanger right here. It gets pulled out. Some of the stream gets pulled out, and then this one goes down into the condenser and condenses with lake water or whatever they're using, cooling tower. And then over here, you pump it, right? So this is another pump I'm going to draw. Goes in. And then after that, there's a lot of variations, by the way. So this cycle is not the only way that closed feed and open feed water heaters look. There are some variations to it, but this is like the basic one. Essentially, then this gets pumped back up to the max pressure, right? Or back up to the beginning. So what I'm saying is that right here, if you drew this on a TS diagram, it tends to look like this. And the reason why I know that is because we have one pressure here, which is pressure 1. This is the highest pressure in the cycle. It's also equal to this pressure before here. Then this pressure is the middle pressure, because turbines, as you run through it, expand, right? It lowers the pressure through it. So we have a pressure 2, which is right here, and then pressure 3, which is over here, which is the lowest pressure. So this is actually a very common setup for Rankine cycles, like all of these state points. Very common. The one over the other one over there is just a P8 or it's an HS version, which HS is something that you don't see very often. So I wouldn't worry too much about this. More or less, this one is probably the biggest one. All right. So let's do general consideration. So it says the properties at states having the same specific entropy can be related using the graphical and tabular property data discussed in 6.2. For example, as illustrated by figure 6.8, temperature entropy and enthalpy entropy diagrams are particularly convenient for determining properties at states having the same value of specific entropy. All states on the vertical line passing through a given state have the same entropy. If state 1 on figure 6.8 is fixed by pressure 1 and temperature 1, states 2 and 3 are readily located once one additional property such as pressure or temperature is specified. So what they're saying is that if you look here, if we say the entropy going into that, remember that first turbine stage I drew over here, if it is equal to some number, and then it is also equal to the second state, right? Like that number didn't change. We didn't add any entropy, right? And no heat transfer carried any entropy out or in. We know that all we have to do is know one of these two values, T2 or P2, and you can find state 2, right? Similarly down here, you can do the same thing, right? Knowing something helps you, and the reason why it helps you, knowing one more thing solves the question because you already know what entropy is, right? So that is what they are saying there. It says the value of several other property states 2 and 3 can then be readily read directly from the figures. And it says tabular data can also be used to relate two states having the same specific entropy. For the case shown in 6.8, the specific entropy at state 1 could be determined from the superheated vapor table. Then, with S1 is equal to S2 and one other property value, such as P2, T2, state 2 could be located in the superheated table. So what they're saying, like I just said, is that we started superheated. S1 is equal to S2. We then look at this pressure and we determine where we are at in the tables. You would say, oh, okay, well, this pressure 2, or this entropy, is higher than the one at this pressure on the saturated tables, so therefore we're superheated. Then we go down again, right, and do the exact same thing with here until we realize that we are now in the saturated region. Until our entropy ends up on the saturated region, then we know we're down here, right? So then it says, using the ideal gas model. So this is the first section we're going to do with entropy through a process, right? Constant specific entropy. So it says, figure 6.9 shows that two states of an ideal gas having the same value of specific entropy. Let us consider relations among pressure, specific volume, and temperature at these states. First, using the ideal gas tables and then assuming specific heats are constant. So we have two ways we're going to do this. So it says, ideal gas tables. For two states having the same specific entropy, equation 620A reduces to this. So if you recall, this used to be delta S, right? Is equal to this. And if it's a isentropic process, that means that delta S is 0, which means you can set this initial equation that you remember, which is these two entropies, minus R ln of P2 over P1, you can set it equal to 0. And then it says equation 640 involves four property values, P1, T1, P2, T2. If any three are known, the fourth can be determined. If, for example, the temperature at state 1 and the pressure ratio are known, so P2 over P1 are known, the temperature at state 2 can be determined from this. So essentially what they did was is they just, you know this, and you know T1. That means that you can have all of these values, and therefore, by knowing all of these values, you would get a value of specific entropy, or not specific entropy, absolute entropy. You would get absolute entropy. And then, because absolute entropy is only reliant on T2, you could look this entropy up on the air tables, and you would be able to correspond it to a temperature, right? So, that is what they're saying here. And it says, since T1 is known, S of T1 would be obtained from the table, and then the value of ST2 would be calculated, and the temperature T2 would be known, right? And it said, okay, so I'm not going to go too much more into this because essentially it's all just equation solving, right? It's all maneuvering the equation and finding the unknown, right? If you know any combination of these things, you will be able to solve for any of the other ones. That's what they're saying, right? Let me see. Okay, so this is important. So this right here is for air. So everyone, this is very important for future classes and for probably this one as well. So air, this is a special case, right? It says for the special case of air modeled as an ideal gas, equation 640C provides the basis for an alternative tabular approach for relating temperatures and pressures at two states having the same specific entropy. To introduce this, rewrite the equation P2 over P1 is equal to exponential. So they just did this right here. P2 over P1 is equal to this, exponential T2 minus T1 over R. And since they are subtracted, you can divide them by exponential rules, right? Algebra. So you can divide them, and that's how you get this. Then it says the quantity exponential S of T over R appearing in this expression is solely as a function of temperature and is given the equation PR of T. So this right here is what we call a, I think this is a reduced pressure, if I recall. I need to make sure that that is what I'm going to say. Oh, it's relative pressure. Okay, relative. Reduced is the other one. It's the one we used earlier in the class. Relative pressure. So what this means is that essentially you can represent isentropic processes of air by using this right here. You can use PR, so essentially P2 over P1, so the actual pressure ratio is equal to PR2 over PR1 because it is only determined by temperature. And what they did was they replaced this whole part with another function. So you remember whenever I told you that U plus PV kept showing up a lot in how they were determining tables? Similar here is that this showed up and they gave it a name, and what they gave it was PR. It was PR for this. And we'll talk about how we use this in practice in just a second. So once again, it says P2 over P1 is equal to PR2 over PR1, and this is for S1 is equal to S2, so a isentropic process for air only. And so anytime you do air analysis of like a air blowing through a turbine, air in a compressor, things like that, you will probably use this right here. So do try to remember that. And it says the function PR is sometimes called relative pressure. Observe that PR is not truly a pressure, so the name relative pressure has no physical significance. Also, be careful not to confuse PR with the reduced pressure like I did just a second ago of the compressibility chart. So the compressibility chart is that other P reduced pressure thing that we talked about a long time ago, but forget that for this chapter. And then it says a relation between specific volumes and temperatures for two states of air having the same specific entropy can also be developed. So what they did was they did the same thing for pressure as for volume. So essentially they made VR, right? So VR. So if you recall, they did a volume ratio instead of pressure. So V2, little v2 over little v1 is equal to this stuff, which they replaced it with VR2 over VR1. So we now have two new concepts, two new table values for air. And why this is important, if you guys remember, when we looked at the air table, which I will go and find, we were right here. Nope, A22, I'm a little off. I've passed it there. So if you guys see here, PR and VR are listed in the table. And so when you have closed systems with like volume changes, so for example, whenever we do in chapter 9, which we don't do it in this class, we do it in the second class, Thermo 2, you do auto cycles and diesel cycles, like car automotive cycles, right? And so you will use VRs for that because you do air standard analysis. So we do it on an air basis instead of like doing like fuel mixtures, which is a little more of a difficult calculation. You do an air standard, you can get a very quick representation of what it might be. And then PRs is for like compressors, right? So once again, it's broken up by closed systems and open systems, right? Compressors being open, closed being like auto and diesel cycles. So these are listed in the tables. And so once again, V2 over V1 is equal to VR2 over VR1, and this is only for an isentropic process for air only. All right. And then we have the constant specific heats one. So this one right here, we don't use this very often. And at least I never did in Thermo 2 or this class. I don't think I ever used this. But essentially, You can, once again, do it with ratios of temperatures and pressures, but there's this value here, this K, and if I recall, K is listed somewhere in here on that. Let me see where it is. I want to make sure I give this right. Variation of CP. No, that's not it. Maybe it is. A21. Let's go there. I think that might be it. Here it is, yeah. So as you guys can see, we have K here. That right there is that K in that equation. So essentially what they've done here is that for these types of questions, what you'll end up doing generally is that you'll do you'll be given some like 2 or 3 of these things or 3 of these things, and you'll have to find one of the other ones using K. But it works the exact same way. This essentially, they are the same way of doing things, except you don't use this one as often. And the reason why is because the PR values are they are done not with constant specific heats, right? This one is done with constant specific heats. And if you remember what I said earlier, constant specific heats, if you have a large change in temperature, constant specific heats of air don't really make sense because you could have, wild changes, right? Now, obviously, sometimes it's not very wild. Like if you have, let's say, 300 to 500, it only went up by, 0.024 or something. But if it's large changes, picking one constant specific heat that is not in between here is not as accurate. But you could also pick one in between and make it accurate, which is what most people do anyway. All right, so, but this one, don't worry. I wouldn't worry too much about this. I don't think you ever get a question that has you use this. I think for most questions, the method in which you will do things is with the PRs. So get to know this more. All right. And then we have illustrations, isentropic processes of air. So it says means for evaluating data for isentropic process of air modeled as an ideal gas are illustrated in the next 2 examples. In example 6.9, we consider 3 alternative methods. So right here. So right here is an example question that we will do really fast. So let's go ahead and open the old Paint 3D, right? So canvas time. Anybody have any questions while I'm doing this? I know it's kind of a lot, right? But we'll get through it, I promise. So all right, so it says air undergoes a isentropic process, right? So air undergoes an isentropic process from P1 is 1 atmosphere and T1 is 540 Rankine. So we were given some things. Once again, guys, we need to first write what we have. This is the importance. So givens. We were given that the first pressure is 1 atmosphere. Now you guys might be like, oh man, 1 atmosphere. What is, we don't see this very often, right? 1 atmosphere is equal to 14.7 psi, or pound force per inch squared, right? It is also equal to it's equal to 100 kilopascals, 101 kilopascals, and also equal to like almost 1 bar. So it's just what you are currently experiencing right now, which is 1 atmosphere of pressure. Okay? And then we were also given T1 is equal to 540 Rankine. So we are in English units, if you guys did not get that. And then it says, and it went through an isentropic process to a final state where the temperature is T2 as 1160 Rankine. So T2 is 1160 R. It says, employing the ideal gas model, determine the final pressure P2 in atmospheres. Solve using PR data from table A22. So this is the first way to do it. And then it's also interactive thermodynamics. We're not going to do that because we don't have access to the software like other people. And then it says constant specific heat ratio, which we might do that one. Really, if we have time, we might do it. But the one that I want you to really know is this first one. So what do? with this? Well, we do basically what we do every time, right? We go to the tables and we find the things that we need to do. So let's go up here and let's write an equation down. So really fast, we know it's an isentropic process, right? And we know it's air. And we also know that we can use the ideal gas model, which means what? So the ideal gas model unlocks the tables for us. Whenever they say use it as an ideal gas, it unlocks the tables for us. So we can use air tables, A22. Although this one will be A22E, the English side. And then whenever they say an isentropic process, it means what? It means S1 is equal to S2, which unlocks us being able to use another set of equations, which was the one we just talked about, which was P2 over P1 is equal to PR2 over PR1, right? Remember, we just saw this equation up here, right? We had just seen this one. This is only for processes of air as an ideal gas and where entropy is constant, which is a isentropic process. So that is our tables we can use. We have unlocked it. Those are the key words that unlocked it for us. Now, let me get rid of this. Now we just need to solve for what we want, right? So over here, well, we were given P1, so P1 is good here. And we were given nothing else. We need everything else here, right? And we are trying to find P2. So does anybody have any ideas about how we would go about this? Let's wake up here, guys. No chatting today. It's Friday, I know, but wake up. Let's see what we got. Anybody have an answer for me? What do we do next? Anybody? Okay, so Tanner is correct. So we need to go to table A22E, which I am trying to get there. A22E, and we need to look up our values on this chart. And so remember, this chart, the fun thing about this chart is that it only depends on temperature. So all you need to do for air, there's like, it's ideal air, it only depends on temperature, which means that we just need a temperature to find everything else. We can find enthalpy, internal energy, all this stuff just with a temperature. So our first temperature was 540, if I recall. I'll be sure about that. 540. So we need to go to the table and look up 540. So 540 is right here. So 540, and you slide across here, and you pick up our PR value of 1.386. All right, so let's put that on here. So 1.386. So state 1. Yes, they don't have any units because they're ratios. All right, so I didn't even write that down, right? PR1 is 1.3860. So we have just looked that up. All good. Then the second one is T2 as 1160 Rankine. So once again, we go right back to the table and we go find 1160, which is right here. Use 1160 and we slide over to 21.18. 21.18. So let's go back. PR2 is equal to 21.18. So 21.18. And now this equation looks a lot more manageable, right? We have P1 already given. We have PR2 and we have PR1. Now we just need to maneuver it around to find pressure 2. So that is the next step. So what we do is we then write out our equation once again with our values in it, and we solve for it. So let's do solution. So let me move this over. So we are trying to find the second pressure. So we have P2 over P1. I'll do it the nice way. Is equal to PR2 over PR1, right? So this is where we're at. And then, if you maneuver this around, obviously you will end up with P2 being equal to PR2 over PR1 and multiplied by P1, right? And so, if you do these and you do this out and you put in our numbers, let me pull out the calculator here. It is here today. You will end up with some answer, hopefully, which I'm going to get. It's going to be a higher pressure. PR2. Sorry, my cat is once again complaining about not being loved every second of the day. And times 14.7. So it looks like our pressure is going to be 224.64 psi. Because I did mine in psi. So let's see what their answer is. So they did the same thing we did. They maneuvered the equation around. They found it. So they did 15.28 atmospheres. So 15.28 atmospheres. So 15.28 times 14.7. Yeah, it's my pressure. They just did it in atmospheres. So this right here is pressure 2. Now this process in which I've just showed you is the basis for solving a lot of these next chapter questions. Not next chapter, but next class mostly. Because what you'll end up with is you'll be given initial conditions generally, like P1, T1, and you'll find PR1. And then from there, you have to use PR2. Like a lot of times they won't give you a temperature at the second state. And you'll have to use PR2. Like you'll maneuver this equation and you'll go, all right, well, P2 over P1. And you have to find PR2. And then from there, you'll find a PR2 value, which in this case it was 21.18. And then from there, you will go find enthalpy. And from there, you'll find temperature. It works a little differently. Most times, you don't get the second temperature. So it's a variation of how you solve it, but it's the same process. Just maneuvering this equation gets you to where you need to be. Like I said, we can just quickly look at this one. So this is part C. So this is with specific heat ratio. Assumed constant, or specific heat's constant. You then just plug it into that equation we saw earlier, which was P2 over P1 is equal to T2 over T1 raised to the K over K minus 1. And what they did was they just went to A20E and they found the middle temperature at 850 Rankine, and they found that K value, and they put it in for here. And then you have the same answer, and you get 15.26. Very slightly different, but both acceptable answers. All right. Let me see if this one's anything we need to really work on. Not really. We could do it though. Let me see. Actually, there was something. Maybe we'll just work on that next time. I'm trying to think about what we want to do today, because this isn't on our agenda here. 6:12. So I think we're. How about this? I think we're good for today. I don't think we need to go any further. I don't want to get too far ahead of the chapter here. This right here is very similar to the last one. So I'm not super concerned about it. Essentially, what all this question is that you just find. You're doing the exact same process. You're able to use PRs, and from here you can find things to find state 2. And then from there, you plug it in, and you can find masses. That's, I think, what the question's asking. Yeah, that's it. It's pretty much the same. It's a very similar question. So I don't think we really need to go too much more in depth into it. So next time that we come back, so you're going to get off a little bit early today, we'll be doing 612, and 612 is the basis for all what you will do in Thermo 2. And I cannot understate that. Like, it is the basis of it. You will be doing isentropic efficiencies of turbines, nozzles, compressors, pumps constantly. All the time. You will solve cycles that have like 8 states, and they will just be, these things will be in there, and you have to know how to solve through them and how to use isentropic states to find the actual states. Because obviously real cycles are not isentropic. So using isentropic efficiencies, you can find the real one, the one that's actually described, not the one that is perfect, right? And so we will get to there next time. Let me go ahead and take attendance for today, and then you guys are good to go. Short video today. Wonderful.